So we'll take a look at the multiple choice review. So number one here, the dot plot shows the miles 28 residents have traveled. So which of the following is closest to the percentile 85? So basically we're looking for this person right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's the 20th out of 28, which is approximately 0.71. So the closest there is about the 70th percentile. Number two, large simple random sample of people 19 to 30 in the state of Colorado were surveyed to determine which of two MP3 players they preferred. So what population can we generalize these results to? And the key is safely. Well, it's such a specific sample, age 19 to 30, and it's those that are just in the state of Colorado. So that's pretty much as far as we can go with it. So only people aged 19 to 30 living in Colorado. Here we're going to be asked, here's the side-by-side box plot, and which of the following statements is true? So this is just a matter, just read through, pay attention. There's a few outliers out here. Maybe I highlight those a little bit, make sure we don't forget about them. But as you go through, the one that is actually true is E, that approximately half of the males in the sample spend as much time in the store as females, as any female, right? Here's half of the males right here, and it is right in line with the maximum for females. So that's the true statement. Just real quick, the range of the amount of time in minutes males is 40 minutes. Well, no, the range for males, don't forget, has to go all the way from, basically it looks like 5 minutes all the way up to 90. So that range is actually 85 minutes. The mean amount of time in males is approximately 20. Well, here's the thing, males is so far skewed. The median is 20 minutes, but the mean would probably be somewhere up here because this data is so far skewed, right? That data would probably have this type of shape to it. The third quartile for males is 45 minutes. The third quartile is the end of the box, which is right here. So there's Q3 for males. So that one's not true. And the interquartile range for the time females spent in the store, there's Q1, there's Q3. So it's basically the width of the box. It's not 15 minutes. It looks like it's more around the 10-minute range. So the correct answer, about half of the males spend as much time as all of the females. We go to the probability of obtaining a head when a coin is flipped is 65%. Which of the following is the closest to the probability that x should be less than or equal to 15? This is a binomial, and it's a binomial CDF because we have this continuous, and so we're flipping it 25 times. The probability is 0.65, and this right now is set up perfectly because remember, binomial CDF and geometric CDF always does less than or equal to, and once you type that into the calculator, we're right at about 37%. Here, a study was conducted comparing birth weights of twins. Mu sub F is firstborn, mu sub S secondborn, and so mu sub D will represent the differences. Because the two things are not independent, right, one can affect the other. This is the perfect situation for matched pairs. And so recall that the hypotheses for matched pairs will be mu sub D, and really there's only one choice for that, and it's either that the two weights are the same, or again, if mu F is bigger than mu S, well, that means that the difference is going to be bigger than 0. It's going to be positive. So the buyer of this electronics store wants to estimate the proportion of defective wireless. So there's 5,000 controllers. The shipment consists of 200 boxes, each having 25 controllers. So the buyer numbers the boxes from 1 to 200 and randomly selects 6 boxes. She then opens the 6 and examines all 25. Well, this is a situation where she's randomly selected the groups and then everything within the group. That's a cluster sample. A distribution is not symmetric. That's important. Which of the following is the best estimate for the z-score? Well, here's my problem with this. If they say not symmetric, Z is out unless N is really big. They don't tell us that we have a large sample size, so the best thing that I can tell you to say is that Z-score should not be used right here. Say that N was big, however, if we did have a big N, if large N, the best way to do this will be inverse norm. And remember, the third quartile is the 75th percentile. And that's how I would do it. Now, that's only if N was large. Sophomore, junior, and senior students at a high school are surveyed regarding potential increase in activity fee. 3 possible responses. They could agree, not agree, or no opinion. They're going to do a chi-squared test to determine whether there's some kind of independence, so the degrees of freedom. Remember, for chi-squared, it's rows minus 1 times columns minus 1. So here's the thing. There are 3 possible choices, and there are 3 classes that are being surveyed, right? Sophomore, junior, senior. Freshmen aren't in there, which is just 2 times 2 for degrees of freedom of 4. All right. Certain type of remote control car has a fully charged battery. They're going to give you a distribution. It looks like the mean is 80 minutes, and the standard deviation is 2.5. So the shaded area, so that's at 80. So if we go up 1 standard deviation, that's 82.5. If you go down 2 standard deviations, that's 75 minutes. So the shaded area would be the probability between 75 and 82.5 minutes. The following scatter plots, which one of those would be r equals -1? Not that this would ever actually happen in the real world, but that'd have to be A. That's a pretty straightforward one. Publishers of this magazine want to determine what proportion of their 50,000 subscribers are pleased. So they are going to mail a survey to 1,000 subscribers selected from those that have received the magazine for 5 years or more. This introduces bias, obviously, right? Longtime subscribers are probably more pleased with their subscription. The best way to eliminate the bias is to go ahead and mail that survey to a group of 1,000 from all the subscribers, new, old, trial subscribers, everything. An environmental scientist here wants to test the null hypothesis that some device is not effective. So if the null is that it's not effective, that would tell us that the alternative is that it is effective. Under which of the following conditions is a type 1 error? Remember that we had our box here, HO rejected, and this would be fail to reject, and then this is which one is true. So if HO is true and we failed and we rejected it, that's a problem. Let me clean that up a little bit. This is if HO is true, right? So if HA is true and we rejected HO, that's why this is a good decision right here in that bottom corner. But for us, type 1 means, where that came from? Type 1 for us means that we will reject the null when it was true. So let's look at the context of the problem. If you reject the null, that means you're going to say it is effective when in fact it is not. And the corresponding answer there is choice A. Here, a data set of tests is being transformed. We're applying that rule, so it's a transformation rule. Which of the following is not true? Make sure you pay attention to these nots, or which it is true, which is false. Read carefully. So mean and median, these are both measures of center. And measures of center are both affected by multiplication, that 3.5, and addition. So those are true. Range is a measure of spread. Keep in mind, spread is not affected by addition and subtraction. So that's the one that is false. Standard deviation, that's a measure of spread. And as you can see, they're not adding the 6.2 to D, they're just multiplying. Measures of spread only by multiplication or division. And the IQR is 3.5 times the IQR. Again, D and E, standard deviation, IQR, are both measures of spread. So they'll be multiplied, but they won't be added. So D and E are actually true. That's the same question. Random sample of 25 households from the school district. Um, in which of the following intervals is the median located? So they've done a really nice job for us to number those. So if it's 25 houses, the median should be somewhere in the 12 to 13 range. And this is just a matter, I know we did this one in class. So there are 4, 5 people are below this, 7. I'm just accumulating these as we go. There's the 12th observation is here, which means the 13th observation is in that particular bin right there. I don't know what it is in terms of age, but I do know it's going to be between 8 to 10 years old. Based on a random sample of these 50 students, we got a 90% confidence interval. Which of the following statements is true? Go ahead and anticipate you're going to get a question like this. You have to be able to interpret the intervals. And it's going to come down to making sure that you understand what's happening. So this one, the problem with A, so for this particular example, remember that's going to be the interpretation. And confidence intervals, we're confident in our method, not in the actual numbers. The rest of these are going to, basically, they're forcing the interval to be stuck, and you're never stuck with your interval. This particular problem is one of the tougher ones on the on this practice test. So 10% of orange candies are orange in this dynamite, and holiday mint candies, 45% are orange. So we're going to take 25 of each, and 1 dynamite mint candy and the other from holiday. So each of them we're going 25. And so what are the expected number in each? So expected here, so we know it's 10% of the 25 and then plus 45% of the 25. And that is equal to, we should see about 13.75 there, so those are out. And then standard deviation, this is where you got to be careful. NPQ, so it's 25 times 0.1 times 0.9. We got to add to it 25 times 0.45 times 0.55. Now, when we're adding standard deviations, remember we actually add variances, and then we got to come back and take the overall square root, and so the final answer here is 29.05. In a random sample of 60 shoppers, 36 said they've been to a movie, and then we got 50 shoppers from a different shopping area. 31 of those said they've been to a movie. So what significant tests? Well, there's 2 things, right? We got 2 different, well, 36 out of 60, 31 out of 50, those are proportions, right? So we have 2 proportions. So that's a 2 proportions e-test. The National Honor Society of the school is going to give a random sample of 100 seniors from all high schools in the state to determine the average number of hours of work, or number of hours per week spent on homework, excuse me. And so they're going to create this 95% confidence interval. At the end of the day, which of the following is the best way to decrease margin of error? Well, the best way to pretty much fix anything, these 2 things kind of repeated for whatever. The best way to fix pretty much any problem in this course is to increase sample size. 90% of people who have a particular disease will have a positive test. All right, this has got tree written all over it. So they have it or they don't have it. And they're either going to test positive or negative. So 90% of the people that have the disease will get a positive result. So if you have it, 90% of the time you'll get positive, 10% negative. 90% of people that don't have it will test negative, which means 10% test positive. And 5% of people have the disease, which means 95% don't. What percent of the population would test positive? Well, here's the deal. There's 2 ways to be positive. You can have it and test positive. You cannot have it and test positive. A lot of folks will probably make the mistake of stopping right there, have it positive. Or you might not have it and still test positive. And by the time, right, have and positive, not have it and positive. And that's going to come out to be approximately 14%. Here's a recent survey. So this is a survey proportion, which means 0.27 is a p-hat. The true proportion is 0.29. For a sample size of 1,000 that are selected, what are the mean and standard deviation for the sampling distribution? So here's the thing. This is by saying if we took sample after sample after sample, well, that's going to start to stack up around what number? Well, it should stack up around the true value. Well, that gets rid of A, B, and C. And then since it's a sampling distribution, we're going to have to use PQ over N for our standard deviation. This is not a binomial. Because we took a sample, right, sample of 1,000, we have to use a sample standard deviation. Marketing company wants to estimate the true proportion of consumers who would react favorably to this new campaign. They want to estimate to have a margin of error of no more than 5%. So first off, I'm seeing margin of error, I see proportion, and I see margin of error. So that tells me right away margin of error with proportions, Z star times P hat Q hat over N. So the margin of error is going to be 5%. The Z star associated with 90, go to your table, 0.645. And then what is the closest N? And now we're looking for a P hat. Well, unfortunately, they never gave us one, so we'll use P hat equals 0.5 to be conservative. So if we plug 0.5 in for P, that means Q is 0.5, and what you're going to end up with is 271. Here in a large school district, 16 out of 85 randomly selected high school seniors play a sport. In the same district, 19 of 67 play a sport. We're going to create a 95% confidence interval for the difference. So this is a 2-prop Z interval. Go to your yellow sheet. You'll see the standard deviation, standard error, right? That's just a new standard deviation, equals P hat 1, Q hat 1 over N1 plus P hat 2, Q hat 2 over N2. So plug in the numbers. 16 out of 85 is approximately 0.188. So there's your Q hat, and there are 85 students in that one. P hat 2, so 19 out of 67 is approximately 0.284, and then 0.716 over 67. You got to take the square root of that. And again, the reason I'm using P hats and not P pooled, right? It is two proportions, but I'm using P hat because it's an interval, not a test, right? You test the pool. This is one of the trickier problems on the practice test here. So the number of points scored in the game, you could score 0, 1, or 2. So each one of them is independent, but what we'd like to do is say we're going to play the game twice. So Y is going to be number of points for 2 games. And this is one of those examples where I would highly, highly, highly recommend going ahead and writing out your possibilities. So you could score 0 points, 1 point, 2 points, 3 points, or 4 points. That's what they're telling us. But in order to reduce some confusion, right, think through, what does it mean if you score 0 points in 2 games? Well, that means you scored 0 and 0. Well, from above, we see the probability somebody doesn't score is 0.4. So this is 0.4 times 0.4. So the probability of 0 points overall is 0.16. Now, 1 point, that means you either went 0 and 1, or you could have scored a point and then scored 0. So in other words, we go 0.4 times 0.3 plus, there's the or, 0.3 times 0.4. And that is equal to 0.24. Think about how many different ways could you score 2 points playing this game. So you could score 2 points by doing 1 and 1, or 0 and 2, or 2 and then 0. If we think about that in terms of probability, that's 0.3 times 0.3 plus probability of 0, remember, was 0.4, and the probability of 2 is 0.3. And these numbers right here, the numbers in these parentheses are coming off of that chart from above. So by the time I sum all of those together, I'm at 0.33. The probability, or the options to score 3 points, you could do 2 and 1, or 1 and 2. So probability is 0.3, 0.3, right? Look back up at the overall, at the chart, right? The probability of scoring 2 points was 0.3, right? Here's 2 points right here, and that probability is 3. So 0.3 times 0.3 plus 0.3 times 0.3, and that is 0.18. And then to score 4 points, that means you did 2 and 2, which is 0.3 times 0.3, which is 0.09. So what value of y is the most likely? You're most likely going to score 2 points. Here's one expected value for a table like this, right? The chi-squared, and remember it's row total times column total. We're actually not going to have to do math here. We're just going to have to go find the values over the overall total. So we want respondents aged 30 to 50. So there's the 108 that prefer green. There's the 99. And the overall total is 314. So we want 108 times 99 over 314, which is choice A. Here's one where we're just going to have to read very carefully about the data to figure out which one is true. So first off, husbands tend to rate the quality of living higher than wives. As you can see, most of the husbands were above a 6, whereas you think, looking at wives, not a lot of the wives were above a 6, so that one's out. Husbands, more overall ratings of 7 or less were given by husbands. No, in fact, it's the other way around. More of the wives were below 7. The range in the husband's overall ratings is greater than the range in wives. Well, think about this for a minute. It looks like husbands go from about 4 to 9, so that's a range of 5. However, wives go all the way from a 9, up here to 9, all the way down to a 2. So for the wives, that range is a lot bigger. That's 7. So this is out. The difference in overall ratings between husband and wife is not more than 3. So this one you got to think about for a minute. But take, for example, that husband. It looks like he was 8, right? The husband was 8, but the wife was only a 3. So that's a difference of 5. So that's out. Which leaves us, for each couple, the overall rating assigned by husbands was the same as wives. That's not true. Excuse me, I misread number 1. That husbands, do rate the quality of living. I mixed husbands and wives up. The correct answer for this one is A. As you can see, husbands had a tendency to go higher than wives. Apologies if that was confusing. A 90% interval is going to be created, but they're going to take their sample size from 9,000 down to 1,000. Well, here's the thing. To decrease margin of error, you want to increase sample size. So first off, we're decreasing sample size, which means our interval is going to get wider. So we can go ahead and eliminate those 3. What I would do for this one, I just plugged in some numbers and tried some stuff. I said, a 90% confidence interval is 1.645. So, if n was 9,000 versus n is 1,000, I just tried a couple numbers. I had a pretty good feel that I knew what was going to happen, simply because, well, 1,000 is 9 times less. You take the square root of 9, it's actually 3. But if you're not quite sure what's going on, they didn't give me a p-hat, so I just picked one. I used 0.4, 0.6, 0.4, 0.6. And what you'll see if you actually try this is the second confidence interval is 3 times wider. So a good strategy for a problem like this, if you're not quite sure what's happening, plug some numbers in. New restaurant is going to determine the best time and temperature combination to roast these 5-pound cuts of lamb. So here's all the options. The quality of the finished product is evaluated for each roast. So which of the following is true? Here, It's a matter of understanding what you're looking at. The explanatory variable is not the quality. This is the response. Quality is the response. So that's not true. The response failure, well, they've just switched these. This is the explanatory. If the experiment is repeated, identical results will be expected. There's no way to know that. So that's not true. There should be a control group. Well, that would just be meat sitting out doing nothing. That doesn't make any sense. What we need to realize is that by doing multiple cuts, that's our replication. Local real estate magazine uses the median instead of the mean. What we can see here, there's a strong skew to the right, which means most of the data, right, if there's a strong skew to the right, is here. So that tells us the median is here and the mean is here. The question, the median is more accurate than the mean, but why? Why is the median more accurate? And that's because the mean is affected by skewness. The director of this fitness center like to examine the effect of 2 exercise classes, gives you some data. Which of the following is a confounding variable? So where is something in there that could cause some effects that we're not accounting for? Really the one that's going to cause the issues is part E. Because both classes were conducted at the same time, that's going to affect who can take it. So, all of a sudden, certain groups are going to be eliminated, right? If it's at 10 o'clock in the morning every day, anyone that works can't take the class, right? So there's where your confounding variable comes in. This particular problem, we'd like to create a 95% confidence interval for the slope of the regression line. So here, right, first off, there's slope, 0.0462. Remember, the slope line is this particular line here. So what we're interested in is b plus or minus t star times the standard error of the slope. Well, we do know some of those already. The slope is 0.04625. We need to come up with a t star, but the standard error is 0.01565. So right away, we can go ahead and get rid of a few of the answer choices. And we're down now to figuring out what's the 95% t star. We're told there are 16 wind-up rubber bands, so n equals 16, which means, keep in mind, degrees of freedom for a regression test is n minus 2. So we need the t star associated with so that'd be inverse t for 14 degrees of freedom, and then also it's 0.025. You could go to the table and we'd find that t star to be 2.145. Recent study conducted to investigate this time required to complete manual dexterity. What is the probability that a mean sample will be more than 11 seconds? So here's the deal. We took a sample, a random sample. So what is the probability that x bar is over 11? So what we need to do is come up with a z-score, 11. The mean is supposed to be 10.2. Here's the trick. The new standard deviation isn't 16. It's 16 over the square root of 144. If you're going to use your normal CDF, which you're going to have to eventually to get that probability, we're going from 11 to infinity. The mean's still 10.2. This is where you're going to have to be careful. Because it's a sample, you have a new standard deviation, and that answer is 0.2743. For this particular problem, based on this data, which of the following statements is true? Just read very carefully, and we'll see that the true statement here is actually C. So, the director here, which of the following statement is true for 100 of these students? Again, read very carefully, pay attention to what you're doing, don't rush through this, but you should find that that answer is D. On their birthdays, employees at this large company can take a longer lunch break. So which of the following is not expected to be part of the process if we conduct the hypothesis test at the 0.05 level? All right, so being willing to assume the distribution is normal. Nope, we need to do that. Knowing there are no outliers, that's important. Using a t-statistic. Well, this is a sample, We don't have a sigma, so we need to use a t-statistic. N is the number of degrees of freedom. Well, n equals 10, which means there are 9 degrees of freedom, which is right. Oh, excuse me. That's also true. If p is greater than 0.05, here's where we would fail to reject. However, this particular part says that we will reject. There's the correct answer for this problem. Dog food company wants to test their new high protein formula on weight gain. In this experiment, they want to reduce variability because of different growth rates. Which of the following strategies is most appropriate? Well, since we know on the front side what an issue is going to be, we're not going to stratify this. We're actually going to block it, and we're going to block based on the breed. This is a good opportunity to block on breed. Different dog breeds grow at different rates, so that would be important. Since we know it's an issue before, that's why we block. Statistics student wants to compare mean times needed to access flight informations on these two websites. They give you a mean and a standard deviation, right? So we got website 1 with a mean of 2.5, standard deviation of 0.8 minutes. Website 2 has a mean time of 2.1, a little bit larger standard deviation. Assuming the conditions are met for inference, which of the following is true about the p-value once you run the actual significance test? Here, I wouldn't go through all the process of doing much more than just realizing this is a 2-sample t-test. Put that data into the calculator, and what you realize is it's a pretty large p-value, and that means there is no significant difference. And finally, the last question here. This histogram represents data obtained about some population. We're going to pick 2 people at a time. What you should realize is we've got a lot of low values and a lot of high values. Now, the central limit theorem tells us that over time, if we keep doing sample after sample after sample, we should get a normal distribution. However, this is kind of a unique problem. This is sample size 2, which means if you think about it, we could get a low and a low. And if you take the average of the low and the low, you should get a low number. You could get a high number and a high number. And if you take the average of the high and the high number, that should give you a high number. The other option is a low and a high number. And if that's the case, you're going to be somewhere in the middle. So basically, we're looking for a distribution with low, high, and middle. And that's right there, choice C.